Hi, and welcome back to this series of videos where we are covering the book Introduction to Robotics from the author Seth Binico. And on the last video, we we end working on the topic 2.4.4. We finished this topic working on the example 2.3. And the first thing that I wanted to do on this video is to correct something that I did wrong, which is the angle between the n-axis and the x-axis. So the example 2.3, it says that the axis n, this one, is in parallel with the axis x, this one. So if I move this axis, you will see that it's in parallel with the axis n from the other referential system. And right here, I wrote 9 degrees angle, but actually when you have two parallel vectors, lines, axes in this case, um, parallel means they are doing 0 degrees between them, and if was 90 degrees, actually they will be orthogonal between them. Okay, so that is the first thing that I wanted to do with you on this video. And 0 degrees angle, as you can see. And now let's move on to the topic 2.4.5, which is the representation of a very rigid body. So let me write this. Topic 2.4.5, representation. Rigid body. An object can be represented in a space, linking a referential on it and representing this referential like x, y, z coordinates and x, y, z system. And an ANO system, and those are referential systems. Once the object are permanently linked on this referential, and let me draw the the figure 2.10, which is the representation of an object in a space. Let me draw this figure. The axis Z, axis X, and the axis Y. And this is an referential system. And we have a vector, which can be an arm, a vector P. And a rigid body, and his referential, let's call, which can be this one, and O. And let me repeat this very important statement. Once this object is permanently linked on this referential system, your position and orientation relative to this referential, it will be always known. On the topic 2, we talk about it on the topic 2.4.1 and point 2. We talk about how to represent points and vectors, and we see that is pretty much the same how you represent a point and a vector. And we just have to remember that a point, it has no size or dimensions, only coordinates. And the idea on the topic that we are seeing now, 2.4.5, is to clarify this sentence. An object can be represented in this space, linking this referential and representing this referential, linking it on it this other referential, linking the A and O axis to the referential system with the XYZ system, referential system. And if we do this, the position and the orientation relative to this referential, the object, the position and rotation will be always known. That's what this topic is telling to us. And we also saw how to represent points in vectors in the matrix form. And for a rigid body is not different. A referential can be represented in a matrix form. In which the region of the referential and the three vectors that represent your orientation in relation to the referential of reference. And at this point, you might understand this statement. It's what we are covering right here the origin of the referential and the three vectors that represent your orientation in relation to the referential of reference. So we can represent this configuration in a matrix form. So we will have nx, ny, and z. This axis ox, oy, oz, 0, and this other referential system ox, oy, oz, and a x, a y, a z, 0, and the vector coordinates. And he keeps saying a point in space, it has only 3 degrees of freedom. So let me illustrate this for you. Let's illustrate a point and a point in space. When we are representing a point in space, we use the x, y, z coordinate system in the Cartesian plan. X, Y, Z, and he says that a point, it has only 3 degrees of freedom. So imagine that this point, it must to be fixed, and it moves only on the z-axis, y-axis, and z-axis. It cannot rotate around the axis z. It cannot rotate around the axis y and the axis z because it don't has dimensions, and it only do this movement. But for a rigid body, so let me draw a rigid body. It can be a cube, I don't know. And this cube, it has 6 degrees of freedom, which means that it can move alongside the axis z, y, and x, and also rotate on this axis, so he can move to this axis and do rotation movement to this axis to this axis. Okay, so a point, it has 3 degrees of freedom, but a rigid body, it has 6 degrees of freedom. And because of this, consequently, all we need to, all which is necessary to define completely an object in space are 6 parameters that describe the localization of the region of the system, um, the localization of the region of the object in the referential system, and your orientation uh, related to these 3 axes, Z, Y, and X. And let me repass this with you. And this last line, it contains the scale factor W. But if I'm not wrong, if these are not W, but he says these are scale factors. Okay, so now we know that a rigid body, it has 6 degrees of freedom. But right here we have 12 parameters. So what we need to do is write equations of restriction. Write equations of restriction. Based in what we know about this referential. So let me copy this figure and paste right here. So let's write 6 equations of restriction. But very important, these equations are based on what we know about this referential system, and we know that the 3 unit vectors A and O are perpendicular to each other. Okay, and A and O, they are forming 90 degrees. In relation to each other. And this so on and so forth. Okay, and also it's important to point that a length of each unit vector represented by his direct cosine and sine must be equal 1. So let's write each one of these equations. The first, and this is the scalar product, which is equal 0. And we read this way the scalar product of n and O must be equal 0. Okay, second one, the scalar product between n and A is equal 0, and the scalar product of A and O also equals 0, and now the length of the vector n is equal 1, the length of the vector O is equal 1, and the length of the vector A is equal 1. Okay, and as a result, he says the values that represent a referential of a matrix in a matrix, sorry, must be such that the listed equations must be true. Otherwise, the referential will be wrong. Okay, for now is all. On the next video, we will apply all this information to resolve the example 2.4. So that's it. Thank you.